Okay, 8.3 talks about isomorphism. There's a bit more to this than what we're going to cover. We're just going to go over the basic idea of isomorphism. This came up in discrete math, and we did the application. Is a lot simpler than what we're going to do here. Here we're just going to introduce it, and we're going to go mainly by definition 1, which says a linear transformation from V to W that is both one-to-one and onto is said to be isomorphic, and W is said to be isomorphic to V. Every real n-dimensional vector space is isomorphic to Rn. Think of Rn as consisting of all of these n-dimensional vector space listed. State whether the transformation is an isomorphism. No proof is needed. We're going R2 to R3, xy, xy to 0. Well, that 0 right there is not onto. Therefore, the transformation is not isomorphic. Okay, well, so check if it's one-to-one or onto. On 4, so given a matrix M22 into R, where R could be anything, well, let's see how this works. What if that is 0? What would happen? So this is not isomorphic because it's not a linear transformation. Now A to its transpose, okay, that is one-to-one and that is onto. So yeah, this is isomorphic. You see transformation. Is isomorphic, or is an isomorphism. Mapping, so all of these into all of those, that right there does not have anything onto it, so this is not onto. Therefore, T is not isomorphic. Determine whether the matrix transformation from R3 to R3 is isomorphic. So here with those, we just have to check really quick if those are, well, here, if I multiply this by -1, don't you get that? Which means the determinant equals 0, therefore they're linearly dependent, those vectors. So this is not one-to-one, and here, therefore T sub A is not isomorphic. Really quick to check. If not, you just find the determinant. 3 by 3 you can tell. How about here? Now, this is where things get a bit more interesting. Find the dimensions of n of the solution space W for Ax equals 0, and then construct an isomorphism between W and Rn. Well, let's do this a step at a time. That is, let's find the actual solution to Ax equals 0. Well, this is fairly simple, because if I take negative rho 1 plus rho 2 in rho 2 and negative rho 3 plus rho 4 in rho 4, and just do a switching, that'll do the trick. Now if I switch rho 2 with rho 3, So here, again, ax equals 0. Keep in mind I'm doing that. So we know that x4 is x4. That's free. x3 is x3. That's free. x2 equal x4. And x1 equal, negative x4. Negative x3. So basically we have negative 1, 0, 1, 0, and 0, negative 1, 0, 1. So here we figured out that dimension of W is 2. So find the dimension of n of the solution of Ax equals 0. Well, n in this case is 2. And construct an isomorphism between W and Rn. Well, let's see how we're going to do that. We're going to say negative x. So one was, I lost it. This was negative x3, negative x4, x3, x4 map into x3, x4. There we go. You could use C and T if you wish. We say this is an isomorphism between W and R2. And that's all we're going to do. We're going to stop right here.